Welcome. Today marks the shift from our study of the derivative in the tangent line to the area under a graph. The goals of this video are to determine the area under a graph and also to approximate the area under a graph using rectangles. In many cases, it's useful and meaningful to find the area under a graph. For example, if a car is traveling 65 miles per hour for 3 hours, the graph would look like this. The area under the graph and above the x-axis would be the shaded region. If we find the area of this, which is a rectangle, which would be length times width, or 65 times 3, we can see below here that the units of hours simplify out and we're left with a total of 195 miles. So this area represents the total distance traveled in this case. Here's another example. This graph represents the manufacturing cost per phone for a certain number of cell phones. So if we take a look at the area under this graph and above the x-axis, we could divide it up into 4 different regions, where each region would be a rectangle, and it would look like this. So again, to find the area of each rectangle, we'd multiply the length times the width. So in this case, the yellow area would be 160 times 2,000. This area would be 100 times 3,000. This area would be 60 times 2,000. And then lastly, 20 times 3,000. So this total area, because we're multiplying the cost per phone times the number of cell phones, would represent the total cost of producing 10,000 phones. Now we could use this information to divide by 10,000 and determine that the cost per phone is $80. All this gathered by determining the area under the graph. Here's one more example. Sunset Nursery determines the cost to grow mesquite trees large enough to sell in dollars per tree to be this function, where x is the number of trees. Now keep in mind, this is the cost per tree, so this would be equivalent to marginal cost, or large C prime of x. That's the reason why they used a lowercase c for this cost function. We want to graph the function, determine the area, and also interpret the meaning. So let's first take a look at the graph. It's a line with a negative slope. Here it is. We have the number of trees on the x-axis, the cost per tree in dollars on the y-axis. Now what's unique about this one is the area under the graph and above the x-axis is a trapezoid. And remember that the area of a trapezoid is given by this formula. So using this geometric formula, we can determine that the area would be 1/2 times base 1 plus base 2. Now if we turn this trapezoid up, this would be base 1, this would be base 2. So base 1 we'll call 50, so base 2 would be 10, and this length here would be the height, which is 200, which is equal to 6,000. The area of this region is 6,000 units, but more importantly, when we interpret the meaning of this, we're multiplying the cost per tree in dollars to number of trees, so we can conclude that the total cost to grow 200 trees would be a total of $6,000. Now the question becomes, how do we find the area under a graph if we can't use a simple geometric formula? If we consider this graph on the interval from 0 to 8 and above the x-axis, could we approximate the area under the graph? Well, one thing we could do is divide the interval from 0 to 8 into smaller intervals and then make rectangles, find the area of these rectangles, and we could say that it would be approximately equal to the area under the graph. We can see that these two rectangles would be too small of an area, but these two over here would be too large, and so it would be very close to the area under the graph. The more rectangles we used, the more accurate our estimate would be. So here's the idea. If we let n equal the number of rectangles that we're going to use, where a would equal 0 and b would equal 8, based upon the interval we're considering, the width of each rectangle would be delta x, which would be equal to b minus a divided by n. So in this case, each rectangle would have a width of 2 units. Once we divide this into widths of 2, we do have to decide whether we want to use the left side or the right side to represent the height of the rectangle. And in most cases, in this textbook, we'll use the left side of the interval to determine the height of our rectangle. Let's take a look at this more closely. If I call the area of this rectangle area 1, area 2, area 3, and so on, we do need just to determine the length times the width. This first rectangle, f of 0, would be the height, and 2 would be the width. And the second rectangle, f of 2, would be the height, and 2, of course, is our width. the third rectangle f of 4, and the fourth rectangle would have a length of f of 6. So we could say our area would be approximately equal to f of 0 times 2, that's the area of the first rectangle, plus f of 2 times 2, plus f of 4 times 2, plus f of 6 times 2. Now remember, to find these heights, we have to substitute these values into the original function here. One way to do this would be to use the graphing calculator to save ourselves some time in the calculations. So if we type our function into y1 and go to our table, we can just type in 0, 2, 4, and 6 for our values of x, and these would be our function values we need to find these areas. You can see I've already done that, so let's go ahead and go back to the screen and write this out. This comes out to approximately 62.8 square units. Now looking at the same problem, if I would have used the right side of the interval to determine the height of each rectangle, you can see the picture would look different, but it still would be a good approximation of the area under the graph. Let's take a look at this problem in another way. This is the area that we actually want to find under our function, but since we don't have the ability to do that, what we're doing is using rectangles to approximate the area under the graph. As we increase the number of rectangles, you can see our approximation gets better and better. And you can kind of get the idea, if n went to infinity, it actually would approach the area under the function. Now these are the left-sided rectangles, because I'm using the left of each interval to find that area, but of course we could use the right and the same idea would develop. Okay, let's go back to our presentation. So again, it doesn't matter which side of the interval you use, but the more rectangles, the better. And so this is our sigma notation, or our summation notation, that represents the area of each rectangle based upon how many rectangles we use. So the definition of area of a region in the plane would be the limit as n approaches positive infinity of this summation, which represents the area of all of those rectangles. Okay, let's try one more example. Approximate the area under the function f of x is equal to 1 over x squared on the interval from 1 to 4 using 3 and then 6 rectangles. Remember, n represents the number of rectangles. So to find the width of each interval, we'll calculate our delta x, which would be b minus a, so 4 minus 1 divided by 3, of course, would be 1. So we'll divide the interval into subintervals of width 1, and in this problem we'll use the left side of each interval. So this first interval, this will be the height of our first rectangle. We'll call this area 1. On the second interval we use the left side. That would be our area 2, and then the third interval, this would be area 3. So we can approximate this area by finding f of, remember the first height would be f of 1 times 2 plus f of 2 times 2 plus f of 3 times 2. So now when you evaluate the function at x equals 1, 2, and 3, that would look like this. To save some time, I've already done this, and it comes out to 4936, which is approximately equal to 1.36. That would be the approximate area under this function if we use 3 rectangles and use the left side of the interval. The last example, we want to do the same thing, but now we want to have 6 rectangles, so n is equal to 6. So our delta x will equal 4 minus 1 divided by 6, which is 0.5. So we need to divide the interval from 1 to 4 into 6 equal intervals of width 0.5. And that would look like this. Let's go ahead and sketch in our rectangles. Again, we'll use the left side. So there's our first rectangle. There's our second, third, fourth, fifth, and sixth. Notice how these rectangles are larger than the area under the function. Sometimes that's called the upper sum. Okay, so our area will consist of 6 different rectangles. So using our graph, we should be able to find the area of each of these rectangles. Let's go ahead and measure it out. It would be f of 1 times 0.5 and so on. Again, we'd have to sub all of these x values into the original function in order to find the height of each rectangle. And to save some time, I've already done that and calculated all this out, and it comes out to approximately 1.024. Since we used 6 rectangles to approximate this area, we could conclude that this would be more accurate than the previous example where we had an approximate area of 1.36 using 3 rectangles. I highly suggest sketching out your intervals, sketching your rectangles, and then find the area of each one to approximate the area. I hope that helped. Thank you and have a good day.